Hello, everybody. In this video, I'm going to introduce you to the concept of spectral classes. Once we had telescopes equipped with spectrometers, astronomers set to the task of looking at all the stars and looking at their stellar spectra, their absorption spectra due to light leaving the photosphere and going through those atmospheric layers. They're a little bit cooler than the photosphere, leaving absorption lines. This is going to be a little bit of a history lesson plus a conversion toward our modern classification scheme, where we're classifying stars based on a physical property of the stars according to their temperatures. And by classifying the stars according to a property of the stars themselves, an intrinsic property of the stars, we're really going to start unlocking the secrets to all the properties of the stars. So these spectral classes we're about to go through are one of the most important things to learn and to master and to understand for us moving forward through this class to understand the stars and really understand the properties of the stars. What makes the stars work? All right, let's go ahead and jump right in. As I was saying, as soon as we had spectroscopy and telescopes equipped with spectrometers where we could split the light out and look at how bright each wavelength is, astronomers went crazy looking at stars, and we started to notice that the spectra of stars are different. Not all stars have the same spectra. We will see later on that they almost all have the same composition, but they didn't know that yet. What they did have were spectra of stars, which they knew somehow related to properties of stars like composition. They didn't know about temperature yet. So at first, they just have a whole bunch of stellar spectra. Look out in the sky, find a star, take a spectrum of it, find another star, take a spectrum of it, and then start looking at all the spectra and try to make sense of them. This was an incredibly difficult task, especially since this is all happening before Bohr came along and came up with this Bohr model of the atom, and we really had modern atomic theory going on. So they were really just trying to look for patterns in the spectra. So here I have 7 different spectra of stars. And what I'd like for you to do is take a moment, pause the video, look at each one of these spectra, and think about like, okay, how might you organize and arrange these spectra? How would you classify them? How would you break them up? I'll give you a moment to do that. All right, I'm going to assume that you paused it and you gave it an earnest try to come up and try to organize these. See if there is something other than the organization I have of A going down this way or going down this way, or maybe you're looking at it this way, or maybe you shuffle it up a bit. Notice that these are in increasing alphabetical order because that's how originally people went about doing this before we had our understanding of the atom, and more importantly, the understanding of how spectral lines form by moving the electrons around through the energy levels of an atom. What people did is they looked at how strong the hydrogen alpha line is here, and then just ranked the stars, called the ones that had the strongest hydrogen alpha line, called those A stars, the ones that had the second strongest hydrogen alpha line, B stars, then C, D, all the way, and they kept going all the way to the letter P. That is a lot of different classes of stars, and all it's doing is ranking them according to one spectral line. Not really that useful. So what ends up happening in the story of this video is we reshuffle this deck of A through P, get rid of most of the letters, and come up with just 7 letters, O, B, A, F, G, K, and M. And we define these 7 spectral classes. This is our modern classification scheme. Maybe this is what you came up with. Maybe it's not. If you studied the notes, I'm pretty sure that you probably did come up with this one. But what kind of patterns exist? What is giving this rhyme and reason to this organization of the classes? Where sure, you have some hydrogen lines, but the hydrogen line in this A star is a lot stronger than it is in the O star. So what is this ranking the stars by? What physical property? And what we will see is that this is ordering the stars from the hottest star, our O stars, to our coolest stars, our M type or M-class stars. All right, so let's get to the task of figuring out why we have this order of O, B, A, F, G, K, M. That's alphabet soup. And yes, it's something you have to memorize. So why don't I try to help you along by helping you understand why these are the names of the spectral classes? Let's go through a little bit of history first. And prior to understanding the atom and having our Bohr model, we were pretty much just left with we have the spectra of the stars. So a natural way to go about this, and this is mostly people at Harvard were doing, they had all these spectra of stars and they just started to rank them in order of how strong a line is, like hydrogen alpha. And you might bring in some information about the other hydrogen lines as well. Here's hydrogen beta. Here's gamma, delta, epsilon, so on and so forth, gamma. Might as well say them all. So here we have the original way where they just took them and they said, okay, we know we have this hydrogen line. Let's just rank them in that order. Call the ones that have the strongest ones, hydrogen lines, A stars, the ones that have the weakest hydrogen lines. Just go through the alphabet until we run out of spectra. And they came up with P, A through P. This is actually going to give us our lettering. We keep the lettering, but we reshuffle the deck to create a more modern classification system that's based on the physical properties of the stars themselves. So let's consider how we might end up organizing and build a classification system that's not just, let's group them only by spectral lines and only pay attention to the hydrogen lines and only rank them in strength of hydrogen lines. Maybe we want to group them by spectral lines, but we want to look at all the spectral lines and try to figure out if there's a rhyme or a reason as to why we see those spectral lines in some spectra, but not others. So the present strength of absorption lines, not only can it reveal composition, but also, if you understand atomic theory, it buries some information as well. And one of those pieces of information that it buries is temperature. So all of these spectral lines have a temperature dependency. How strong the line will appear, so how broad and dark is, say, the hydrogen alpha line, depends on the temperature of a star. And people started to figure this out. People like Annie Jump Cannon at Harvard really started to figure this out, that there is this temperature dependency. And it was really by understanding the Bohr model of the atom and knowing that these spectral lines are caused by electrons moving around within the atom. So let's imagine a really, really hot scenario and a really, really cold scenario in on the surface of a star. So let's make it really, really hot, say like 30,000, 40,000, 50,000 Kelvin. In such a hot environment, all the atoms there are moving around really fast. They have a whole bunch of energy. In fact, they have so much energy that the hydrogen there is ionized. They've had the electrons stripped off the hydrogen nucleus. So now you just have hydrogen nuclei, protons, and electrons. Well, if you don't have an electron hanging out in the atom, then you don't have an electron to move through those energy levels, so you're not going to get hydrogen lines. And this explains why, perhaps our hottest stars, our O stars, as we'll see, they have weak hydrogen lines because they're just hotter. And that means that the hydrogen is ionized, and therefore you're not going to get hydrogen lines, which require the electrons to be a part of the atom. Now let's go to a really, really, really cool scenario. So if you go to a really, really cold surface temperature of a star, say 3000 Kelvin, then everything's moving around much slower. The energy is a lot lower, and it's a lot harder to get those electrons out of that ground state. Remember that the hydrogen lines, the Balmer lines that we see with our eyes, the ones that we're looking at here in these spectra, they're all transitions from the first excited state to the second excited state in absorption, or the second excited state to the first excited state in emission. We're looking at these in absorption. So in order to get an electron to go from the first excited state to the second excited state, you have to get it out of the ground state. The cold stars just simply aren't hot enough for it to have a lot of hydrogen atoms that have electrons out of the ground state. Therefore, you don't get hydrogen lines there either. There's a sweet spot somewhere around the A-type stars with surface temperatures around 10,000 Kelvin. And this is true not only for hydrogen atoms, but for all other atoms. And since every atom has its own unique set of energy levels, electron energy levels, you got to play this game with all of them. Turns out in helium, it's a lot harder to move electrons around. You need a lot more energy. So you don't even really see helium lines until you get to really, really hot stars. So there is a temperature dependency. So perhaps what we want to do is not rank and order the spectra of stars according to just the strength of the hydrogen line, as we just saw, that varies with temperature. You don't see it for hot, you don't really see it for hot temperatures, you don't really see it for cool temperatures, you see it in the middle. So maybe what we should do is just shuffle all the spectra and order them by temperature. And this is exactly the way that we come up with our modern classification scheme. This is why we have the letters in order of O, B, A, F, G, K, and M. We break them into 7 different spectral classes. That's easier to remember than all the way out to P. And then we rank them according to temperature. And we can do this thanks to actually understanding the Bohr atom and having modern atomic theory, where we know that you're really moving these electrons around, and that's what gives rise to the spectral lines. And that's connected to the temperature. The person that figured this all out was Annie Jem Cannon, one of the coolest names in all of astronomy, opinion, not a fact. She's the one that connected atomic theory to the stellar spectra that everybody was trying to rank and organize and try to classify the different types of stars that we see out there according to their spectra. She realized that the strength of the lines depends on the temperature. And if it depends on the temperature, then you can make a ranked list of these spectra from highest temperature to lowest temperature. So she's going to drop the excessive number of all the way A through P because nobody wants to deal with all that. And then she's going to re-rank everything according to temperature to give us our modern day classification scheme that is called the Harvard classification scheme because it was developed at Harvard. And in 1924, she published this work that reshuffled the deck. We kept the letters, but we got rid of all the extra letters and then reshuffled the letters around so that the hottest stars were ranked as the hottest, and then we go to the coolest stars. The letters that remained were O for the hottest ones, then B for the next hottest, A, F, G, K, and M. So the hottest stars, the coolest stars, the 7 spectral classes. And we'd say things like O star, A star, M star to refer to the types of stars. Or we'd say an O-type star if you want to be really formal about it. You know, so whenever you're hobnobbing with your stellar scientist friends, your stellar astrophysicists, now you can communicate in their language. Yes, you are going to need to know these in proper order from hottest to coolest. I recommend coming up with a mnemonic. I do not recommend the classic mnemonic. It's very dated. We'll leave it at that. You could use a mnemonic. Game of Thrones was popular whenever I was first making these slides. So I came up with a Game of Thrones themed one of, oh boy, another fine game of kings and men. Come up with your own mnemonic. I think I'll start a Canvas discussion on this where you can post the mnemonic that you come up with, and maybe I can finally have one that I really like and I can use for this class because I'm not super happy with the Game of Thrones one either. But you should know these in order from hottest to coolest. And now we can take a look. We can rank these stars from hottest to coolest. Our O stars will have the highest surface temperatures, all the way up to 30 to 50,000 Kelvin. And our coolest ones, our M-type stars, have temperatures of 20 or 2,600 to about 3,000 to a little shy of 4,000. Notice that there's a range of temperatures for each one of these spectral classes, almost as if broad brush strokes of 7 classes to define all temperatures between 2,500 and 50,000. 7's not going to be enough. We're going to have to get a little bit more detailed, which is where I'll go next. But I want you to go ahead and take a look at all the spectral classes of the stars on a single plot. I think this is an absolutely beautiful plot. I wish I had a really, really high resolution, high quality one of these, and I could hang it as a poster in my office, maybe even in my home on my wall. But here you can see the hydrogen alpha line weak for the hot stars. We understand why now. Then it reaches its maximum strength in the A stars, and then it gets weaker. You can see that as you go cooler, you're getting things like sodium lines coming in. You're getting molecules, so molecular lines coming in, titanium oxide. Cooler temperatures allow you the formation of molecules, so you start to get these broad molecular lines. For the hot stars, you can see you can start really moving around things in the helium atom, so you can get some helium lines. So you can see the variation of all the different spectral lines. And thanks to anti-jump cannon, we now rank these according to temperature. So we have a rhyme and a reason. We connect this to a physical spectral, a physical property of the stars. So notice this means you can go to the telescope, measure the spectrum of a star by which uh, absorption lines are there and how strong they are. You can classify it. You can look and go, oh, it's got some sodium lines in it. It doesn't really have very strong hydrogen lines. It's got some magnesium lines. It got some iron lines. Oh, this one looks like it's a K star. And all of a sudden, you know what the temperature of the star is. I want to go ahead and show you what these things look like graphically as well. So astronomers, while these are really, really pretty pictures, if we were to go across each one of these and measure how bright each color is, how bright each wavelength is, and plot that up where a bigger, higher on the y-axis would mean it's brighter, then we could create a graphical version of spectra. So these spikes down are absorption lines. So I just wanted to show you what these look like graphically. And now you can actually see a little bit of rhyme or reason. You can actually see the temperature dependence here. Because if you remember Wien's law, that the higher the temperature, the shorter the wavelength peak. Oh, you see that it's moving to longer wavelength as you go to cooler and cooler stars, almost as if all of these things connect to one another, almost as if the universe is governed by physics, a natural set of rules and laws that if we can understand, then we can use that to understand the universe, including the properties of stars themselves. And that's what this figure is all about. So let's take a look and start making the connections that we're going to be talking about as we continue our discussion on stars in later videos. So here is our ranking of stars, our spectral classes, our 7 spectral classes from the hot ones to the cool ones. We have our O stars, B, A, F, G, K, and M. Hottest surface temperatures, coolest surface temperatures. There are other spectral classes now, the L, T, and Y. These are brown dwarfs. Some Ls are probably are stars. Some early Ls are stars. But you don't need to know these. These are newer ones. We pretty much 4 stars, O through M. You can think of brown dwarfs as failed stars. We'll get there later this semester. But now, here we have a plot, or a figure, I should say, a picture of the spectral classes O, B, A, F, G, K, M. And we're looking at the stars themselves scaled appropriately in size and given the appropriate color, roughly the appropriate color that the eye would see. So we can start seeing that the properties of stars are connecting to one another, that this ranking, this of spectral class by temperature is also a ranking by other properties. And if we have connections between one property and other properties, that means there is some physics behind all of it, some rhyme and reason to nature that'll allow us to translate from one physical property to another physical property. So these spectral classes are really opening the door. They're our gateway into really getting after the properties of the stars, because they're all connected. You can see here that our O stars are blue in color. Reminds you of the photometry video that I had. And that's because if you look at their spectrum, they're giving off a lot more blue light than they are red light. Why are they not purple stars? Well, this comes down to, let's see, it's called chromaticity, I believe. It's how our eye perceives color whenever you have all of these different wavelengths coming in. And we just don't see purple very well. And whenever we see all those wavelengths coming in and that rough ratio that you have from O-type stars or B-type stars, our brain interprets that as blue. So you can see that our O stars are blue stars, our M stars are red stars. So we can connect the temperature to color. We can see the O stars are big and bright. Let's go with the bright part first. So these are the most luminous, these are the least luminous. O stars are the biggest, both in size, so diameter or radius is how we really talk about the size of stars, and in mass. So biggest and most massive and most and brightest, smallest, least massive and least brightest, dimmest, lowest luminosity. So notice that if you know the order of the spectral classes according to temperature, you also know the order of the stars by their spectral class, relating that to, say, the mass, the luminosity, the temperature, the color. All of those things, since you have you can rank them, and this ranking holds over various properties, really tells us that there's something underlying here. There's some underlying physics where if we can understand it, then we can use these spectral classes themselves to get at all the properties of the stars that we're interested in. And this is why understanding these spectral classes is so important. Now, I want to end this video by, and before I go to this plot, notice that we have a lot of temperatures here. And notice that we have like a B0, a B5, an A0, an A5. What's up with that? 7 classes is not enough for the huge range of temperature of about 2,500 all the way up to about 50,000 Kelvin. 7 samplings within that range is not enough. Surface temperatures can be any temperature. So just the broad brush strokes of 7 classes is not going to be nearly enough. What we need are some subclasses. So we can add some additional information so we can really narrow in on the actual temperature of the star rather than, somewhere between 30,000 and 50,000 Kelvin. So the way that we do that is Annie Jump Cannon came up with not only the letter class, but a subclass, then gave that subclass a number where the number is telling you the temperature within the broad spectral class of O star or B star or A star or M star. So we'll say we have, say, A star. That tells me that tells me what a spectrum looks like. It gives me a broad temperature range that that star is. But then we can go even finer and say that A0 stars are the hottest of the A stars. A9 stars are the coolest of the A stars. So we can attach a number to our letter class, or spectral class letter, 0 through 9, that gives us additional information about the temperature, such that 0 is the hottest, 9 is the coolest. And a picture is a lot better to see this. So here's the A stars, where A0 would be the hottest, and then the next hottest would be A1, A2, A3, so on and so forth. When you get to A9, what is cooler than an A star? O, B, A, F. So you go from an A9 to an F0, F1, F2, F3, so on and so forth. If we want to move in the hotter direction, what's hotter than A? O, B, A, so B. So we have A0, what's slightly hotter than an A0 star? A B9 star. So now we have a much closer ranking of a continuum of temperatures. So we can really go, oh, well, that's an A2 star, and A2 stars have this temperature. And yes, you can get good enough where you can look at spectra and not only tell if it's a O, B, A, F, G, K, or M star, but get a good guess just at first glance using just looking at the spectrum of what subclass it is. It takes a lot of work and you have to stare at a lot of spectra. So I don't expect any of you to really stare at spectra for days on end, so you can do that. But I just want to let you know. Also, if you're going to be hobnobbing with your stellar scientist friends, the people that study the stars, some additional terminology. So these lower numbers, the hotter numbers, like the zeros, ones, twos, we have this weird terminology where we call those the early types. So we might want to say, hey, that A1 star, that's an early A, is maybe how it's referred to. I know it's a little bit weird, but this is the terminology that people used. You put a bunch of people working in the same place, Harvard, and they're working on the same problem. They're going to come up with their own terminology. And since they're the ones that came up with it, guess what? We all adopted it. And then the cooler ones, so the 7s, 8s, and 9s, we would call those the late types. All right. we know spectral class. I have one last thing that I'd like to share with you all. On this long, from O0 all the way to M9, which one is the sun? The sun is what spectral class? So our sun, based on its temperature, and yes, the solar spectrum does fit the spectral class. So you can look at those Fraunhofer lines, and you could classify the sun this way. The sun comes out as a G star, so O, B, A, F, G. So it's on the cooler end of things. And within the Gs, it is a early G. It is a G2 star. It's a pretty hot G star. So yes, I expect you to know the full classification of the spectral classification of the sun. It is a G2 star. G stars are sometimes referred to as yellow dwarfs, M stars as red dwarfs, O and B stars as blue giants. All right, that's what I had for you for spectral classes. Thank you for tuning in. We will continue connecting and understanding all the properties of the stars in future videos.